Okay, yeah, so my name is Andres, and today I'll be talking about reading RNTuple data with Uproot. So here's the outline of the talk. So first I'll give some brief introduction and motivation for RNTuple, and I'll describe what's the status of RNTuple support in Uproot. Then there's going to be a brief hands-on demo. So if you want to follow along, you can click on the link on the Indico. It runs on WebAssembly, so it's a nice way to play around with it. And then I'll conclude with some words on future work and outlook. Okay, so first of all, what is RNTuple and why should we even care? So RNTuple is a modern serialization format that will replace TTree. So as you might know, TTree has been around for like over 25 years, and it's sort of like the standard way of storing data in root files. But it's going to be replaced for a variety of reasons. It has become pretty outdated and bloated by this point. So there's lots of inefficiencies. For example, it uses big endian, whereas modern memory layouts use little endian. So there's a lot of switching of bytes and stuff like that. There's inefficiencies, for example, storing and reading nested or jagged arrays. There's lots of special cases and hack implementations. All of these things make it virtually impossible to fully support in Uproot. Is a rough diagram of kind of like the current situation. So there's not really a RNTuple or sorry, a TTree specification, but within the things that root supports, Uproot supports reading a good fraction of it, but there's still quite a bit that it doesn't support. And even within the things that it can read, there's an even smaller set that it can write. So it's sort of like a not ideal situation. Whereas RNTuple it's much more modern and it's going to bring many improvements. The design is much more simple, and there's actually a formal spec, which is really nice. It's focused on native or primitive data types. So, I mean, you can still have structures and classes and stuff, but everything should sort of like boil down to native data types. It uses a columnar layout, which is actually very similar to Awkward, which makes it very nice to sort of like switch back and forth between RNTuples and Awkward. And it is much faster, and it is designed for parallelization, which is something that wasn't thought about in the TTree days. And so all of this should make it possible to support almost 100% on Uproot, both for reading and writing, which is going to be really nice. Here's just so you have some idea of how it performs. Here's a comparison between RNTuple TTree and some other formats. So here RNTuple, you can see that it really shines in modern storage systems like SSDs. And it even outperforms some of the other alternatives by quite a bit. So this image is taken from this paper, and there's a lot more information in that paper, so you should take a look if you're interested. As for the timeline, so the development started back in like around 2020, and the idea is that around now is like when the transition period is going to start to happen. So they're encouraging people to start using it, not for like real data that like should be preserved since the specification is not even final yet, but they're encouraging for people to start trying it out and see if they find issues or if there could be further improvements. And the plan is that the specifications should be finalized by around the end of this year, and then starting next year, hopefully more things start to use it, and then, well, after some transition period, the tree should just be dropped entirely. Again, it was taken from this paper. There's much more information there, so you should take a look. And so the idea is that we'll try to keep up with the specification changes and be ready for version 1.0 when it releases, so that we can support, well, as much as we can. So now let's talk about RNTuple in Uproot. So the initial implementation was written by Jerry Ling. That was about 2 years ago, I think. It was actually fairly complete for reading, and it even had some basic writing support. But earlier this year, there was a significant update to the RNTuple specification that completely broke the implementation. So we had to fix it and rework some stuff, adding some new features that they added. This is roughly the current status. So there's the RNTuple specification. Root still doesn't support all of it, but it supports most of it. And Uproot supports a slightly smaller set, but we're working on getting it as close as we can. But well, I mean, you'll notice here that reading is still not supported, and that's still something we have to work on. I'll talk a bit more about that later. We're aiming to have the same, or at least a very similar interface to the one for TTree. So ideally, people will not really notice that the format changed and the transition will be pretty smooth. But I guess we'll see how that goes. So let's look at a concrete example so that, I mean, it's easier to have all this, to like look at all this in a more concrete example. So let's say we have some data in the following form. Let's say we have 5 events, and for the events we have some trigger, missing ET, and lepton IDs data. So for this one is a Boolean. This one, it would be a struct of 2 floats, and this one would be a vector of variable length. So the example is based on a talk by Jerry Ling, which is really nice, and you should take a look if you're interested again. So the way this would be represented in an RNTuple would be something like this. So here at the top, we have the top fields. So instead of the T branches, the new sort of like terminology is field. So this would be the 3 things we defined. You'll notice here that since this met is a structure, it's going to have subfields associated with it. For this trigger, since it's just Boolean data, it's going to be just directly associated with a column that is what actually contains the data. And then similar here for ET and phi. Whereas for here, since it's going to be a jagged column, we're going to have some offset column that contains sort of like where the data starts for each event. And then here we're going to have an associated anonymous field that in RNTuple are just underscore and then some number, which will actually be associated with the actual data of this field. And we'll see that this actually very closely matches the data layout in Awkward, which is, I mean, what I was mentioning before, that's what makes it easy to go back and forth between the two. So we can take a quick look at the root code that will produce an RNTuple of like this. So I included some example RNTuple.c file. Let's see. Where did it? Okay. So you'll see that here we're importing this RNTuple model and writer. So over here is where we create the fields. So you'll see that we have a Boolean field, this met field, that is this structure that we defined over here. And then this std vector field over here. Then, I mean, I'm just generating some fake data around here, and just filling the tuple over here for each event. But now let's actually look at how we would read this data with Uproot. So as a quick reminder, you can install Uproot simply by running pip install Uproot, or if you have Conda, you would do it like this. Since this is, if you're using this Jupyter Light notebook, it's already going to be installed. So we can simply start by importing Uproot, and then let's open this example RNTuple.root file. We use this f.class names is gonna tell us what it has inside. So you'll see here that it has this NTuple class name or class with of type RNTuple. So you'll see here that it's still experimental, but later on, once it's finalized, it's gonna be just root RNTuple. If we So let's take a quick look at the data layout so you can see how it matched with the graph I just showed. So in order to get the tuple object out of this file, we simply do it like this with the name over here. And then what we're gonna do here is we're going to loop over the field records and just print some basic information. So you'll see here that we're gonna have the trig, met, and lib ID fields, which I mentioned above. And then we're gonna have these subfields, ET and phi, which you'll see here that the parent ID is 1. So that's the way you see that it's associated with a struct, and they're not like top level fields. And then here you see that we have this anonymous field that is actually what it also contains the actual data of this field over here. Now as for columns, it's also what I mentioned above. So we're gonna have 5 columns. I guess here it's a little hard to tell what they are, but you'll see that they're associated with this field over here. And then these two, and then this one, and then there's the offset column. So you see that everything is kind of like in the diagram I just showed. Let's see. Okay, so now what we can do with this is actually put the data into arrays. The way we'll do this is simply doing a double that arrays, and then just printing what this arrays object is. You'll see that it's so it has length 5, and it has this structure over here. And we can check that the memory layout actually matches or very closely resembles the one in RNTuple by doing arrays.layout. So here you see that it's a very similar design where, let's see, so for this one it's just very simple, but for example, for this one there is a jagged array. It's a similar design where it has an offset column, and then the actual data is stored in a different column. So that's what makes it very easy to go back and forth between RNTuple and Awkward. And of course, since we're only changing the way we're reading things after we put everything into arrays, now everything is just gonna work in the usual fashion. So, I mean, we can just get a specific field with that, and then the name. And yeah, so this was obviously a very simple example, but we can actually already read pretty complex files. So here's an example of a file that was produced by an Atlas workflow. So it's stored over here in GitHub, and we use it for testing. If you're using it directly on your computer, you can simply open it like this, just upload that open, and then with the URL here. I noticed yesterday that it is a little broken in WebAssembly. I'll fix it at some point. And for WebAssembly, apart from that, we also need a couple of workarounds. And there's modern browsers have CORS protection. So we need to use a CORS proxy, which, I mean, you should be careful when you use one, but in this case, well, it should be fine. So what we're doing here is we're first downloading this file over here, and then we're just gonna open it as a local file. Then we can look inside. So here you'll see that we're gonna have a ton of TTrees, but then over here at the bottom we have some RNTuples. So we're gonna be looking at this collection tree RNTuple. So here we get this tuple out of this file, and then we turn things into arrays. Oops. Let's see. Why didn't that work? Oh, okay. We're just running. So here you'll see that it's a pretty complex file. So it only has 10 events, but here you'll see that there's a ton of different structures. There's a bunch of different jagged arrays and all sorts of things. But everything already works, and you can read all the data out of it correctly. So yeah, so it's working pretty well. And let's see. Okay, so we also have some good performance on when reading large files. There's an example here with 100 megabytes. If you're running it locally, you should just run like this. I'm not gonna show it here because I also noticed yesterday that in WebAssembly, it's pretty slow. Still not sure why. I think it's probably the decompression, but I'll have to look into it. So I'm just gonna skip this, but just for like a rough number, this 100 megabytes, it has 4 million events, and it takes about a second, well, a bit less than a second to turn it into arrays. So that's pretty good. Okay, and again, since basically what's only changing is the way we're reading things, the rest of the interface is just going to be the same. So the interactions with the rest of the scikit-head ecosystem are going to be unchanged. Oops. Yeah, so for example, here we can make a histogram of the data as before. So it's just normal as before. So now let's briefly talk about the future work and the outlook. So although the RNTuple reading already works, there's still quite a bit of work that needs to be done. We still need to implement some missing features and see if we can implement some well, some things that root is able to read that we still can't read. We were planning on implementing lazy reading with Dask. That's how it was done for TTree. This is especially important if you're going to be working with really big root files. You wouldn't want to just read everything at once and then like dump everything to memory. Our double writing still doesn't work. So it hasn't been fixed since it was broken. And even then, it probably needs to be heavily rewritten, probably to make it simpler. We're trying to keep up to date with the changes in the RNTuple specification, and we're hoping to have it pretty much fully supported by the time version 1.0 comes out. I guess we'll have to see if that works. So I guess the moral of the story should be that Uproot is going to become even more useful than it is now, since it should support almost 100% of the RNTuple specification. So the goal is to have something like this where the overlap between root and uproot should almost be the same. So then uproot would be a very convenient way to read and write files a good authority to read. It would be probably, well, it's a bit slower since it's in Python, but of course you wouldn't have to deal with installing and doing all these things in root, which can be a little annoying. So it's going to be really convenient. And yeah, that's it for this talk. I will answer any questions if there's some, and thank you.
Yeah, thanks a lot. So this is very interesting, and of course, I'm pretty happy to see that you can now read Atlas light files for Atlas produced RNTuple files, and it actually works out. So this is really great. Are there any questions? We have time a little bit for discussion. Since no one at the moment raises hands in the audience, so one thing I remember from reading TTrees with these especially these very large n-tuple files with a lot of branches, there was quite a lot of overhead in Uproot reading, just getting the information which branches are even available in the file took already up to a second or something. It seems to me that this overhead is also gone with our n-tuple. Can you confirm this?
I mean, so I don't know exactly how it works for TTree, but for RNTuple, it's definitely very organized. Like you have like a header and footer that are, well, pretty descriptive, and I think it should be really quick to read what the information is in the RNTuple.
I think Jim has a comment to this.
Yeah, this is a follow-up. So if your question is about the speed of uproots in interpreting the metadata, not the data themselves, but the metadata, when you have, say, 1,000 columns, what the RNTuple reader is doing and what the TTree reader is doing are pretty similar. They are using Python to interpret, bytes, byte for byte, and you would have the same order of magnitude performance. The RNTuple being a simpler format, maybe it would be a less deep call stack, so it might end up being faster for that reason. But it's not. There's a fundamental slowdown in reading this metadata from it being Python, because in order to read 6 bytes or something, you have to say struct.unpack the 6 bytes. It goes through a Python instructions to call the thing that's going to interpret the 6 bytes, whereas equivalent C++ has already read those 6 bytes, in a nanosecond or so. So that much is different. Metadata is interpreted with Python, and that there's the speed hit for that. The thing to do, though, is to try it out. It was something like a second, you said, for TTree. Suppose that for RNTuple, it's the same order of magnitude and it's 200 milliseconds. Experientially, that could be a big difference. So it's worth just trying it.
There's a question or comment from Lindsay.
Yeah, just more of a comment, but this brings back into mind the discussions over librntuple and possible bindings to C++. If there's anyone in the root team in the audience, or if y'all know anything, it would be really interesting to hear what direction things have gone with respect to that. Having essentially a separate underlying librntuple library that we could package and ship with Python libraries.
I think it was called libmini RNTuple.
Okay. All right, that's the only update I've heard, that it's libmini RNtuple now, but that means something's evolving.
No, that's not a change.
Oh, okay. Okay. Do you guys, or Andres or anyone else, do you know anything about where that's going?
I don't know.
Okay, thanks.
For the audience, but years ago, it's 2019 at least, the original plan was that the RNTuple interpreting part of root would be kept separate, would be compiled separately, so that it would be a C++ extension, but it wouldn't depend on all of root, and it would be more pip installable. But that I haven't seen any development on that since 2019.
Okay. Yeah, it seems at the moment also no one in the audience can say anything to this, so let's just see how this goes. But yeah, at least I'm pretty excited to see we can read this with Uproot nonetheless. So that will be very great.